All right. Hi, I'm David Joseph, and I'm going to talk about how we can take any black box machine learning model and figure out why it's making the predictions it's making and the decisions it's making. And before that, we're going to dispel a couple myths. First of all, one myth is there's a trade-off between accuracy and interpretability. They're not. They're independent. Interpretable models can be highly accurate. Black box models can be wrong. Then stemming off of that is that complex models have to be black boxes. They don't, and we're going to show in this presentation several tools to look into these black box complex models. Anything from like an SVM or random forest all the way to like deep learning and AutoML to see why they're making the decisions they're making. And why does this matter? Well, the first thing is bias. So I think we all know that learning algorithms can be biased, even when there is no intrinsically biased variable such as gender, race, disability status, something like that in the data set. The bias can be encoded in other features in ways that are mysterious. Or not mysterious, but not apparent. And this is a big problem. You don't want to be the one deploying a model that discriminates against a group. So one thing is, if before you deploy your model, if you can look and see what features it's considering, and look into more into the really important ones, you can probably catch these biases before you deploy your model and discriminate it against some people. Second one is the acceptance of ML, and this is one I don't think we think about enough. In our communities where like in school or with your coworkers maybe. Or like for me, like on Twitter, in general, people are okay with machine learning, accept it, and like maybe not trust it because I think we're all a little cynical, but like in general, we do accept and believe in machine learning. But that's not the case for the whole world, for the real world. So like let's imagine that you're at a company. Your boss has worked at that company for like 18 years, and he's done things the same way, and he knows it in and out. And one day you walk up to your boss and you say, "Hey, boss, I'm going to, instead of doing things the tried and true way that you know so well, I'm going to use a random forest, or I'm going to use an SVM, or whatever, a multi-armed bandit model." And you do that, he's just going to laugh you out of the room. He's going to tell you to do your work like everyone else, the way everyone else does it. Like, don't fool him again with this crap. Instead, if you got your work done, and then you built your cool model that you're excited about, and you fiddled around with all these tools that I'm going to show you, and like learned how and why it's making the predictions that it's making, you could then kind of humanize the model, because they'll see like, oh wow, this model considers this important. I do too. He somehow relates to it, and this is something that will humanize it and let him to be understanding of your attempts to use it. And then like another example is, let's consider self-driving cars. So which would you rather get in? A self-driving car that's completely autonomous and that's it? Or a self-driving car that's completely autonomous but tells you why it's doing what it's doing? So like, for example, your car stops in the middle of the road and it says 70% chance of a kid running across the street. I'd rather get in that one. That one feels, even though they might have the same underlying technology, that one feels safer. It feels like it was tested more. It feels like a little scary and somehow a little more human. And so being able to see what's going on will lead to whatever technology being more accepted. The last one's a little scarier, and that's AutoML. So for those of you who don't know, AutoML is this new thing that data scientists are doing, where they're just automating away the role of data scientist. Automating away, but basically they're developing algorithms that not only optimize hyperparameters, but also optimize, they actually choose and build the models from scratch. And not only that, they'll do the feature engineering, like all within the algorithm. So that's a lot of the data science workflow right there. And so one thing I think we all need to be thinking about, one thing I've thought about a lot, is how do we stay relevant if AutoML just really suddenly takes off? Like, how are you going to keep your job? And I think this is like an amazing way to do that. So, like, if you can take this ultimate black box AutoML model and you just start feeding it data and playing around with its predictions and getting to understand what's going on inside of it, and like why it's making the decisions are, and like all these things I'm going to show you will work with any model that makes predictions. So that's not a problem. But if you can fiddle around and start understanding like intuitively like what the model is doing, then you'd be someone who can troubleshoot and debug that when things go wrong. And you can also help sell it to customers. And I think that's really powerful and something that's going to be really valuable no matter what happens in the field. And so let's talk about some tools. So the first tool is, I think, the simplest one and one that's going to feel very familiar, and that is variable importance. Now, one reason I personally love tree-based models is because, I can spit out that little, like, Gini importance plot. That's pretty nice. But, the variable importance doesn't have to be limited to tree-based models. We can actually do it for any model that makes a prediction. So we can do that for all models. And how we're going to do this is we're going to use this sort of line of thinking, and we're going to say, if I replace some feature with noise, how much worse will my model be? So, like, what will my new loss be? So basically, we're going to formulate this mathematically now. We're going to let L, squiggly L, be the loss with the original features untouched of your model. Then let's take one of these features and we're going to replace it with noise. And what we're going to do, we're going to sample the marginal distribution of it, which basically means just its distribution given, like, ignoring everything else. So independent of everything else, the distribution of your variable. And with enough data, and like you're going to have enough data, we can just do a permutation of it and call it. That is plenty good enough. Then we're going to calculate a new loss. We'll call it L star of I. I being within this set of features, and that's giving the new loss. That's giving me the loss with the noisy version of the feature. Variable importance is the loss with the feature replaced with noise divided by the original baseline loss. So algorithmically, we're going to fit a black box model F to our set of features X. We're going to calculate the baseline loss for I, and then for each of these features, we're going to replace Xi with the scrambled version of Xi. At the permutation, we're going to just be sampling this marginal distribution over here. And then we're going to calculate the variable importance. And we're going to do that for each feature. One idea, since we're adding, replacing variables with noise, one thing that we could do for a baseline, which is always important to have baselines, is say, well, what if I just added noise to my model? Like, how much worse would it be? And then you could, from that, you could say that any model which is less important than just pure noise is probably useless. And you can get rid of those. So this is an interesting approach, and one that is recommended by Jeremy Howard, who's the author of like PyTorch and FastAI and all that. So pretty smart people do this. So I'm comfortable recommending it. And so what we have here, before I get into it, I'm going to talk about what's in our data set. So our data set, and I'm going to direct you towards this purple plot. Our data set contains 6 features. And what we're trying to predict here is in thousands the number of crew members required on a cruise ship, given the weight of the ship, the number of cabins in thousands, the number of passengers in thousands, the length of the boat in boat length units, the age of the boat in years, and the passenger density, I think, in percent. And from knowing about this data set and from having played with it a lot, I know as a fact that tonnage is the number one most important variable here. especially in the random forest, but also in the linear model, and also in KNN. And cabins is the second most important variable. Like far and away, these are the two most important variables. So what we have here is the permutation importance plot of a linear model of KNN and of a random forest. And so we're going to be looking a lot at this random forest. So I'm going to direct you there first. And I said that cabins was less important than tonnage. This doesn't really give you that level of granularity, but we can see that tonnage and cabins are the two most important features according to our permutations using the random forest. And this is over like 100 permutations average, so I'm going to trust this. Whereas our linear model, yes, cabins is important, but due to the weirdness of correlation, tonnage is not important. That's a big thing to notice. When in reality, if you look at the significance of each of these variables using like stats models or something like that, tonnage is actually more important than cabins. And with KNN, tonnage is important, and it's going to be important for all of them. So this approach in general is a pretty good baseline, and like if you're just going to whip something up real quick just to like kind of make a guess at what the importance of your variables are for any model, you know, including like deep learning or something like that, this is a pretty good try. It's not great. It's going to get some things wrong sometimes, especially when there's correlations, which I'll give you all a hint. Cabins and tonnage are highly, highly correlated. But it's not a bad little try, and it's very simple, and it makes sense. So yeah, permutation importance is a pretty good tool. The next tool we're going to look at is partial dependence, and in this section we're going to introduce some notation, which I'm going to be using a lot. So I'd pay attention, and what partial dependence is basically saying or put it into perspective of these boats, because I want you all to be thinking about the boats. We're going to say if cabins has value, 23, what will, on average, for every time that the cabin is 23, what on average is my model going to predict? So let's formulate that. Let's consider a set of features, of k features, in the black box prediction function, f hat of x. And then here is some important notation. And what I really want you to remember is this underscore s and underscore c. We're going to say zs represents our interest set, which means what we're calculating for. So in this case, cabins, and zc its complement. So that means not cabins. So cabins, not cabins. ZS, ZC. All right. So what we're going to define the partial dependence of our black box function as the expected value of our function using ZS and ZC given all the values of ZC. So that means, well, let's formulate this some more. We can turn this expected value into an integral, which is just given the probability distribution of ZC, what is the expected prediction of our function, also using ZS. And if we put this into a finite sense, we're getting the average prediction of, ZS representing like one observation ZS. We're getting the average prediction of ZS for all of the values of ZC. So again, algorithmically now, so let's say we have n rows for I in n observations. We're going to copy our entire data set and, ignore this and think cabins. We're going to replace all values of cabins with, and let's say that the first value in our data set of cabins is 23. We're going to take our whole data set. We're going to copy it. We're going to replace cabins with the first value of cabins with 23. So the whole cabins column is now 23. We're going to then predict using that new data set. Then we're going to say that's the average prediction when cabins is 23. So pretty intuitive. All right. We're going to just calculate the average prediction given all possible values of everything else. And we're going to do this for each variable. And this yields these pretty plots. And so like just so we can get a feel for interpreting it, let's look at down here this cabins variable. cabins at 9, right? When we have 9, well, really 9,000 cabins on our cruise ship, requires about 9,000 crew members on average. Okay? So that means when our model, like this is of a random forest, and when our random forest sees, oh boy, like there's 9 cabins, which really 9,000 cabins, it's going to, in general, like a very good guess of what it's going to predict is going to be something around 9,000 or 9 crew members. So that's pretty nice and actually pretty useful. And one thing we can think about is how can we use this further? Like we've got this really interesting curve of the average prediction, and one thing we can logically think is more important variables will probably have more change in the average prediction, right? They should be less flat. And so what we can say is that the variable importance with respect to partial dependence is the standard deviation of these curves. Or, in the case of categorical features, the range divided the number of levels. And one thing that we should notice and we should remember, again, tonnage and cabins are most important. And we just did average with a whole bunch of crazy observations. And let's see how the importance works. Oh no, this is horrible. Look at this. Let's look at this random forest, because this is the one that we're going to be talking about the most. What are the 2 least important features? Tonnage and cabins. Oh no. What just happened? Why is this going on? Let's go back. Look at this. Tonnage, cabins, most important. Tonnage, most important. Cabins, most important. But tonnage and cabins, not important at all. What on earth is going on? Right? Something is horribly wrong here. And I promise that the math is right. This is how they actually calculate partial dependence and partial dependence importance. But age is really important. Let's look at age on this original plot. Age is less important than noise. Alright? Age is a terrible predictor. Yet, age is the most important predictor using partial dependence importance. So, why is it failing? And I'll tell you why. It's because cabins and tonnage are highly correlated. And what does this mean? This means there's unrealistic observations present. So that means we're calculating using some crazy observations. And so let's say I learned this with respect to an apartment data set, which I'm going to use that example. So let's say you have a data set where we're trying to predict the price of an apartment. And 2 of the variables in there are the size of the apartment in square feet and the number of rooms. The size of the apartment in square feet, let's say that's going to be reasonably correlated with the number of rooms. So what we're doing in both of these previous 2 algorithms is we're actually calculating the prediction at values such as a 270 square foot apartment with 20 rooms. That's ridiculous. It's going to be all walls, but I mean, that's kind of the case here, right? Which we see with the permutation importance. That we are still calculating some of those weird values. But with partial dependence, we're actually calculating way more and actually strengthening that effect, which is why we see this here. When actually, it's pretty interesting that age and length are always up there, because those are 2 of the ones that are least correlated with other variables. And so, intuitively, when we average the effect of some variable x, which is correlated with variable z, if they're correlated, we're also measuring the average effect of z across x. So what does this mean? This means that if z and x are negatively correlated, that actually the effect of z is going to cancel out the effect of x and hide our importance, right? So that means if tonnage and cabins are negatively correlated with each other, they're actually going to leak in and cancel out each other's effects, which is pretty bad, but makes a lot of sense. So how do we resolve this? Well, we're going to learn about another tool called ICE, which stands for Individual Conditional Expectation. And ICE is super simple. It's the same thing as partial dependence, but we're not going to do any averaging. So if we look at our partial dependence algorithm, imagine this, but we're going to get rid of this step, right? So all we're going to do, I'll show it on this nice ICE slide. For each instance in our set, so let's consider XS. For each observation in XS, we're going to place all the values of XS with XS of I. Then we're going to make a prediction F hat of XS, comma, XC. So we're just to make a prediction. So, and what we're going to see, you're going to see what I'm talking about before I just lose myself in thought. What we get. So basically, we're doing partial dependence. We're doing this, but we're not averaging anything. And this is really cool. So what we see here is each one of these series represents an observation. So this is saying this top series, given a set of XC of not cabins, right? Or this is cabins out here. Given a set of not cabins, right? One row of not cabins. This is what our model is predicting for every single possible value of cabins. That's cool. That's really cool. And each one of these represents a row over all values of cabins in our data set. And what's the first thing that jumps out at you here, or to me at least, and the thing that this can be really useful for, is not so much that, there's no calculations you can do on 200 lines on a screen. That's just not going to happen. But we can very easily see that there is something weird going on here where we got these big jumps right here and here. And what these jumps mean when you look at these ice plots, and this is a great use of these ice plots, is it means that there's some sort of correlation or some sort of interactive effect going on here. And that's what's causing these jumps to occur. So what does this mean? Well, so now we can also see how partial dependence failed with correlation. So we've got correlated values, which gives us these jumps. And with partial dependence, we're going to average all these curves together. And we do that. We go up to 4 here and to 6 here. When we average them together, we're going to average this down to, right about 0. Which is going to make the importance of partial dependence, if we're using the standard deviation, it's going to make it pretty small. So we're actually averaging away all of the interesting parts of our data set. Same thing with cabins. This gap is right around 0.5 or something like that. When we take the average, we're going to condense everything down into one small, not wavy line. So everything is canceled out because of this correlation. And this is why the partial dependence failed. So let's try and think of a way that's a bit more robust. So let's consider each one of these lines, every single one of these lines, and we'll take their standard deviation. So that means that at observations where our prediction is pretty dependent on our feature, it's going to have a very wavy little line. And on observations where it's not going to be very wavy. And if we average all those standard deviations together, or the per curve standard deviation, we can get a really good estimation of dependence or of importance, which is somewhat immune, relatively immune to correlation and interaction. So we're going to average the per curve standard deviation. Or, for categorical rows, the range or the number of level. So, for each one of these curves, take the standard deviation, save them all in a vector, average the vector. So, now, here we go. We've got a pretty good variable importance estimate. So, let's look at our linear model. It's got cabins, passengers, and length as the most important variables, and tonnage right here. So it's still not great, but linear models don't work very well with correlation, so that's fine. But let's really look at this random forest. And we can see, look, tonnage, most important. Cabins, next most important. Everything else, not that important. And you know what? This is actually almost exactly what the variable importance plot from the random forest with trees looks like. So we've got a pretty good, pretty robust way of calculating variable importance and of detecting interaction with these ice curves. The problem with these ice curves, though, is, if you got like 1,000 lines on a screen, that's not that useful. Well, like, I can't really do any mental calculations. I can't explain it to anybody else. I can just say, look, there's a gap here. Something weird's going on. I think there's correlation. And, you'd be right that there's correlation. But they're not intrinsically useful. And the only thing that we can derive from them is this partial dependence, which is definitely not that useful. So, and I mean, we can get variable importance too, which is pretty useful, but we want to do more than that. So, we're going to talk about, now we're going to talk about ALE, which is accumulated local effects. And why are we talking about this? Well, first of all, no more apartments with 200 square feet and like 20 rooms. Second of all, we can easily identify interactions. Third, it's completely robust to correlation. And fourth, which is not on the screen, but it's really, really flexible, and we can use it in a lot of cool ways. So it's a lot more involved than the other ones. So we're going to talk about some concepts. So the first one we're going to talk about is a marginal distribution versus a conditional distribution. And basically, a marginal distribution is a distribution independent of all the other variables. So if we're holding x1 constant at 0.75, the marginal distribution of x2 is this. So it's just the distribution of all the x2s. So nothing crazy there, new there. It's an independent distribution. If we look at the conditional distribution, which is the probability distribution of x2 given that x1 is 0.75, this defines, like realistic distribution of values right there. Okay, so the next intuition we want to develop is, let's consider we have two strongly correlated variables, x. We're going to say, I'm going to call this xs and xc just to be consistent. And let's let f be a black box function with accept these variables yielding a prediction, and assume we are interested in the effect of xs on our prediction, and we have this conditional distribution, or we were able to calculate, which we always are. So we're going to say that this right here, f hat of xs, represents the dependence of f on xs. How do we calculate this? The first thing we can try is we can try averaging. So when we average them, we're not really doing anything about the influence of xc or x2. So that means that we are basically actually calculating the effect of x1 and x2. And if they cancel out, they cancel out. This is what partial dependence is doing. Even on a conditional distribution, this is still an issue. So instead, let's try differencing. So let's break our interset xs and our not interest, so cabins and not cabins, into xs, xc. Let's break it into k neighborhoods. So let's look over at this graph on the right. We got 1, 2, 3, 4, 5 neighborhoods. K equals 5. And we're going to bound them by z of k minus 1, comma s, and z of k s. Z of k minus 1 s and zks. So what does this mean? So right here, in neighborhood 1, k equals 1. That's what the number in the parentheses is. The lower bound of this is z01. So that means s represents just what dimension it's bounded in. So it's bounded in the dimension of x1 here, or of xs here. And it's 0. So n minus 1, or k minus 1 is the lower bound. And zks is the upper bound. So we're going to partition our data into k neighborhoods. Then, for given a xc, so given the rest, so we have a neighborhood bounded by two values of cabins. For each observation in there that doesn't include cabins, we're going to calculate the prediction of our value on the lower bound of xs and xc, and on the upper bound of xs and xc. So that means what we're going to do is, for each y value here, or value of x2 here, we're going to calculate the prediction. So let's just consider this line right here. We're going to calculate the prediction with x1 equal to this, given this y value, x2 value, and x1 equal here, given this x2 value. And then we're going to difference them away. And what this means basically is xc and xc, so, lower bound of cabins of the neighborhood, or upper bound of cabins in the neighborhood, lower bound of cabins in the neighborhood. We're changing that, and we're holding the rest, everything else, constant. So that means when we subtract them, these effects are going to cancel out. So that means we can define the local effect of xs on f as the change in our prediction. Okay, that's it. So it's just going to be the change in prediction, and especially if we make these neighborhoods infinitely thin, right? So if we had like 1,000 neighborhoods, we could generate a pretty dang good estimation of the local effect of xs. So now let's formalize that. So first, let's formally define the local effect. So the local effect of feature s, given xs and xc, is the change in prediction in respect to xs. So that means, again, just like here, it's the change in our prediction if we change this a little bit. So if we change xs a infinitesimally small bit, the local effect over that little bit is equal to that. Is equal to like the change in f given a tiny change in xs. All right, and this makes sense when you think about how partial derivatives work. If you have a partial derivative and it's got two variables, and one of the other variables is of the first order, when you take the derivative, or of any order, when you take the derivative, you just treat this guy as a constant, and you derive him away. So same thing, we're subtracting away, we're deriving away, we're getting rid of our variable that we may or may not be correlated with. So we're actually completely isolating xs. The next thing we're going to do, so right now we have this for one variable. Now let's expand it throughout the neighborhood. So we're going to calculate the probability weighted average of these local effects. So which means basically we're going to take each one of these, right? We're going to take this local effect here, this local effect here, this one, and we're going to add them all together, and then we're going to multiply it by the conditional distribution. So let's look at that just in math form real quick. We're going to take all of them in our dxc, so that is dxc for given all these. We're going to find all of them, and we're going to add them together, and we're going to multiply it by the conditional probability distribution. That's it. It's very simple. So again, we're going to calculate local effects of this observation, local effects of this one, local effects, add them together, multiply by conditional distribution, and then we're taking an integral too, but that's basically what we're doing. The next step is we're going to accumulate the local effects off of the set of partitions ZS. So that means basically, right? We're going to take this little guy right here, or this one, and we're going to integrate it from ZS0 to XS. So what does that mean? We're going to integrate it from here all the way to the end of the plot off the screen, somewhere way off far away. So basically what we're going to do is we're going to calculate the probability weighted average for the neighborhood, right? So we're going to take the local effects of each one of these observations, average them together, weighted by the conditional probability distribution. Then for each one of the neighborhoods, we're just going to add them together. Pretty neat, pretty easy. Now then, to make this something that we can interpret, the next thing that we're going to do is we're going to subtract a constant, so they're centered at 0. So we can see the actual change in our prediction. And this is AL. So the AL value of XS is, again, first things first, it's changing our prediction with respect to, oh, there's a typo there. No, there's not, with respect to, with these two bounds right here. And then it is multiplied by the probability distribution and all averaged. And then we're going to integrate that across the and all the neighbors. So again, we're going to calculate the local effects of each one of these observations. We're going to average them in this neighborhood given the conditional probability distribution in this neighborhood. And then we're going to add them all up for all the other ones. Then we're just going to subtract a value to make it centered on 0. Now, this is pretty intuitive, but also pretty complicated. And in estimating this, it's a lot more complicated. So we're going to give some notational background first before we get into it. So consider a finite set of j-dimensional values. So that means we have a matrix with rows 1 to I, and rows are going to be in parentheses at the top, and columns are going to be at the bottom, and they're going to go to j. M parentheses I represents the value of m across all dimensions or all features at I, and mj represents all observations of m at dimension j. And then we're going to do some basic set theory notation because it scared me when I first saw it, and it'll probably scare you. A backslash, which we'll call it's a set difference, so we'll call it a set diff. A set diff B is the set of all lowercase a that are in uppercase A, but not in uppercase B. So it's everything but. So basically, if we go back and we consider XS and XC, this can be written as XS X set diff C, or X set diff S. It's the complement within a set. So again, if our target variable is mj, m set diff j is everything but j. Or, cabins, not cabins. And then let's also consider, just for a little bit of notation, that we have k neighborhoods or partitions defined within M. These neighborhoods are bounded, as we talked about earlier, by zk minus 1 and zk. Zkj describes the bounding box of the neighborhood k in the jth dimension or feature. So zkj, that defines one of these guys. Z neighborhood j. Okay, so now we're going to estimate it. So the first thing, we're going to start with one observation. We're going to expand. We're going to calculate the local effect of our variable in our neighborhood of our set of x. So we're going to calculate, the effect of on these two bounding of the upper bound. Right, this is the prediction on the upper bound, given cabins and not cabins. And then this is the effect, this is the prediction of our lower bound, given cabins and not cabins. So again, what this is showing here is we're going to, for this plot, calculate, we're going to take this value, we take this value of x2, or xc, we're going to push x1 all the way over here, calculate the prediction. Then we're going to push x1 all the way over here, calculate the prediction, take the difference. That's what this scary looking crazy equation is doing. Next, we're going to average this through the neighborhood. So for each observation in this neighborhood, right? So for each 1, 2, 3, 4 observations in this neighborhood, we're going to calculate this local effect, which is, finitely defined as this. And we're going to average them. And that's all we're doing. Again, very scary notation, but we're going to average them. Then we're going to accumulate the local effects through all the neighborhood. So, we can't do integrals in real life. So we just sum. Right? It's very simple. We're going to sum from k. We're going to sum through the neighborhood. So again, local effect, average per neighborhood, accumulated. Local effects. That's it. And then the last thing we're going to do is we're going to actually take the mean of each one of these, and we're going to subtract that from this. to get our AL value centered on the mean, centered on 0, which means we can interpret it. Which means we can interpret it, so let's say that xj equals 3, and that the AL value of that is minus 5. What this means is that when variable xj is 3, the model is going to predict 5 less than the average prediction. And that's pretty powerful. So let's look at these AL plots and get a little practice interpreting them. So let's look at, for example, passengers. So if passengers equals 30, on average it will predict 1 or really 1,000 less crew members are going to be on that cruise ship. That's what it's, or 1,000 more, my bad. Same thing with cabins, our favorite variable. If cabins is 20, or 20,000, then it's going to predict on average like 2,400 or so. Or no, it's going to predict 2,400 or more crew members are present on that ship. So that's pretty cool. That's pretty useful. So again, this interpretation, very simple, and it's very readable, especially going back to those ugly ice plots. Like, look at this and look at this. This is so much nicer. So I mentioned earlier that we can easily identify interactive effects. And we're not going to get into the math that I've already been talking for forever. But we can do it in 2D. And this AL plot, this plot right here, is showing the effect of just the pure, because with AL we isolate things. This is showing the pure effect of just interaction between cabin and tonnage on our prediction. So that means, basically, and we can look at it a little nicer here. When tonnage is high and cabin is low, we get this very strong effect, a very strong interactive effect. So this means that at like a very high 130, like very, very high value of tonnage and a very low value of cabins, we're going to get some pretty strong effects. That's going to have an influence on our model. And the nice thing about this is, let's look at it horizontally. If the two variables don't have any interaction, you won't see anything here. It'll like, if you look at it heat map wise, it'll all be just blue. So that's the way we know. We can just plot, all combinations of variables, and you can see pretty quickly, oh hey, there's no interaction here. Oh hey, there's interaction here. So again, so the next thing I'm going to do is we're going to view how these local effects work using a single new observation, and this is really, really cool. And this is something. This is what I'm going to leave y'all with, because I think this will get y'all really thinking about what you can do with this stuff. So what we're going to do, I generated a new observation with very reasonable values, and we're going to calculate using the local effects of each of these values. We're going to calculate a prediction. So we're going to start with our mean. We're going to add in the effect of age, then the effect of tonnage, then the effect of passengers, then of the length, then of cabins, passenger density. Then we're going to add in the interaction effect between cabins and tonnage. And we've plotted these all on a nice scatter plot. So I'm going to let it reset and save my voice for a second. But this is really cool. So we start with the mean. Then we add in the effect of age. Then we add in the effect of tonnage. Then we add in the effect of passengers. Then we add in the effect of length. Then we add in the effect of cabins. Then passenger density. Then the interactive effect. That's pretty cool. So we can actually construct a prediction from the mean prediction using the local effects of each one, because these local effects are completely mathematically shown to be independent of each other. And this is really, really, really cool. I think this is incredible. So yeah, you can actually see exactly how a prediction has come to. And if you're doing classification, right, instead of these values between like 8 and 11, this would be 0, this would be 1, and you would actually be able to see how each observation affects the probability of your predicting some class. And that is so cool, and that is so useful. So like, again, in our example of talking about the self-driving cars that say like, oh yeah, there's a good chance there's a being a kid. You could not only have it say like, oh yeah, I saw that there's a 70% chance of a child, but like, here's what part of my camera like detected that. That's really cool. Just using like, hard to code, but fairly simple, intuitive algorithms, we can actually discover and build from just observations a prediction, like piece by piece. That is so cool and so powerful, as we can actually really see how our model is working. We have, how each variable changes our model, and we could probably do a bit more with this, or maybe even consider calculating importance with that. We can also, calculate the importance of models using ICE. And we can see how all our predictions affect everything. We can calculate, and these are really calculated, the effect of pure interaction, which is really cool, just using predict functions. So, right, our interaction function, right, let's look at our two values. We've got 122 tonnage units, 6.87 cabbage units. So let's look here. So 6 is about here, 122 about here, and that's going to change our thing by like maybe 2 or 3. Not 2 or 3, a very small amount, but it's probably going to lie like right around here in one of these low spots. But yeah, basically this has a pretty strong effect, which is really cool that we can see that and we can identify that. And like, if you look at the output of your code, you can really quantify this. And like, if you want to go crazy, you can even integrate Monte Carlo into this AL calculation to sample the conditional distribution and get an even better estimation of literally just the interaction. This is so cool. I'm sorry, but yeah, this is, I just think, incredible and like really powerful and useful. So, in conclusion, interpretable machine learning will keep you valuable. Permutation importance is a great baseline to kind of understand your models. Just stay away from partial dependence. It's not useful, like at all. Because in the real world, there's always some correlation. And yeah, just stay away from it. AL is really awesome. The one warning I'll give with AL is, from a software engineering perspective, it's not. So permutation importance, partial dependence, ICE, you can probably implement like 5 minutes. AL, there's actually only 3 existing implementations of AL out there. Like one by the authors of AL in R, one by the authors of AL in Interpretable Machine Learning book, and one by a group of people on GitHub. So AL is something that it's a bit harder to implement, but it's faster than the others. And yeah, AL is great, but I would recommend using a library because it's pretty painful to try and write the code. And if you can't get your hands on like an AL library, or just on like, or figure out how to code it, because like it's definitely doable. ICE is totally acceptable, but you just have to be careful with correlation. And here are my references, and with that, I'll let everyone go.